You started recording. You can go ahead.
Thank you very much. So now we are recording. Let's continue. Thank you very much, Atem. So I first started generating code, I think, at third year of my study, because there were, of course, interesting exercises to be made. One of them included making a short program that examines the packets from the internet and printing what is the protocol type for each packet and size. I tested it in C, of course. So in C, it's like you see here. You just write the source to file, and then maybe you call the compiler. I used it to dump a list of protocols in RFC because I didn't really have patience to enter all of them by hand. Of course, this solution had big issues. It didn't include any error checking. Here, the entire code was hardwired. In my case, there was a hardwired RFC input file. And when you try to look at the error messages that you get when a compiler will tell you there is something wrong with generated code, of course, it's very hard to find out where the original problem was from. And you have no validation with source code AST, nor any type checking, right? All these things are recommended to be done when you are generating code. Just make sure that you get errors as early as you can. You get errors that reference the original source code that you put as an input. And if you write a plugin, you also should type check that your plugin returns the right. And of course, nowadays I generate code in Haskell, since Haskell is actually one of these languages that are much more modern and have much better code generation and code analysis facilities. Not just talking about pattern matching, and you will see it further in this presentation. So now the first example, the same example written in Haskell. So you can use the package hint, which is Haskell interpreter, to load any Haskell module. Here we also have the source hardwired, just plugin that adds two numbers. So we write the file with plugin HS, we run the interpreter, and then we interpret the simple expression and tell what should be the return type. It's still not secure. And indeed, in most cases, code generation, if you are executing it later on, will be insecure unless you check, and we need to be careful about it. But the security is not the first pain point that you see. The error messages will never reference the source file. And they may be. So first, we want to find the message, where the message comes from, right? Because here we have very short module that we generate. However, in practice, for example, if you take a few thousand lines of XML schema file, and from this you generate many more lines of the parser for entire XML schema, then you will have very, very large files, and you would like to reference the original source file when something is not going right. It's not uncommon when you are analyzing the input or source code in any way to find the bugs in the source code that were missed by the original authors because you are analyzing it in a different way. And the same happens for the code generators. If you generate code from the other language, then it is common that you find new bugs. Just the same as the compiler that is a different compiler for the same language may find new bugs in your source code. So that's not usually called incompatibility. That's actually a bug in the source code. The source code should be unambiguous. So in C, you have this kind of directive that allows you to insert into target language, target code, the indication of where the original input came from, right? So here, if the target is C, we use C preprocessor directive. In case the target is Haskell, we have compiler pragmas, because we would like to avoid any kind of preprocessor directives in C. Does not always happen, but we will try to do it. So for this, we have pragmas. They are parsed by the compiler and they are safer. So you can indicate the line and the column where the original expression, for example, came from. That's very useful if you are debugging a big grammar in Happy or Alex, which are basically parser generators from the grammar. And usually in the grammar, you also describe with expressions what happens with the AST to get AST constructed during. So here you just prepend it to your source code where it starts, right? Here, in case you don't know Haskell, we use operator that is basically merging two things together. That's called semigroup. And it takes two things. In case of strings, it's string concatenation. In case of list, it's list concatenation. And in case of source location, you merge it probably a bit different way. So first, if you check that the file name is the same, then you will take the first line number. But that doesn't really tell us where something that is in 20th line of the whole expression happened, right? So instead of source locations, that is just a line in the input file, we may want to use source spans, which is basically where the code, the source code started and when it ended in the source file. And then we propagate these source spans over all code generator, just like in a GHC. I recommend that you forward this information through macros and analysis. It may be used downstream in the second compiler maybe that you run. You always can refer to user initial and original user input, because long compiler pipelines that include, say, GHC, then assembler, code generator from GHC assembler, and then linker will have a lot of stages, and sometimes the mistake at the very initial stage will present itself at the very final. So now, what happens when you have like 20 years of using the same code generator? And in this case, it's source code generator for another language. So, or maybe the same, or maybe you just generate the Haskell code, right? So imagine you have a situation where you have XML parser, and this XML parser is generated automatically and updated each time the XML schema is updated by, say, W3C consortium or original author of the schema. Then we also need to indicate it in the target file, since ideally, if you are generating code, then the newly created file is only touched by your code generator. That's the holy rule. You have either entire file written by a human or entire file written by a code generator. And you should mark this that are written by code generator so that human never touches it, because otherwise you have very, very cryptic problems where parts of the system are updated and parts seem to be invulnerable to updates and fixes from the human, or human can try to fix the generated code, which of course doesn't work because you will regenerate it anyway, right? You will regenerate it later and fix all the bugs back to the errors. So that's important. I recommend that you always prepend the generated files with a clear description. If you generate entire package, then you add it to README. Just like, for example, in case of Amazon and Google packages that have a clear indication where it originally comes from. And then you redirect the user to change, to induce any changes in the original source. Otherwise, it will not work. So the second thing is, my apologies for the mistake on this slide. What happens when you have a bidirectional code generation? Basically, what happens then is that if you update, like in here, you have a plugin AB equals A plus B. And A plus B may be an expression that is given to you by the user in the original input, right? So what you would like often, in case it's the same or similar language in the input and the output, right? That may happen if it's literate Haskell, for example, that is weaved from different fragments. Or it may happen when it's Alex or Happy. Then you would like user to have an option. Most code generators do not give you that option, but sometimes you can give the user the option to backport the changes from the final source, the final generated code, sorry, to the original source. For this purpose, there is the technology that's called a bidirectional code generation. You may have heard a lot about bidirectional transformations. That's the same. Basically, detect, you insert the marker. In our case, it may be our line marker that indicates that the original input is not from this file, it's from somewhere else. And then you slice these fragments and compare the fragments that you have generated and the fragments that were in the original file. And then you can backport it. Of course, that means that you need to backport the expression. So you need to have bidirectional transformation between these inserted source language expressions and the target language expressions. What you can observe is that often you have partial bidirectional transformation, so you can sometimes allow it to happen. And that's sufficient in practice for small code. So here we have a start marker, which is basically comment and equals, 3 equals sign generated from main HS. And then after we put the input expression, we put the end marker that will allow us to strip the changed code from generated code. Example of a program that works this way is Entangled, which is literate Haskell programming system that is also a universal literate programming system. So you can use multiple languages in a single project, weave them together, and then you can change the generated code, as well as you can change the source document that is actually supposed to be readable. It's in another technique for bidirectional code generation is a syntax-aware code generation. So again, you will strip the slice of code from the generated code and put it back into source, right? You modify a source. Usually it's not used, but sometimes you may find it useful. In this case, if you have a syntax-aware code generation, you basically add some special type of expression In our case, it will be just identity function, which is called original source. This identity function will have a dummy argument, which is source location, which will be put into generated code. And this source location can be later on used to know where to put the resulting expression in the input. So if you have a resulting expression in the parentheses, then basically if you have an AST parser, then you can extract this expression. Whenever there is a function original source, then you treat it specially, right? That requires some kind of either extended syntax facility or a result identifier that you can use for this. There are some languages that allow you to put pragma on every expression or a annotation on some kinds of expressions. And then these expressions can be then bidirectionally transformed forwards and back again. It may be useful in case of, for example, literal programming system, where you are not entirely sure what happens, and maybe a literate programming system is not aware of the syntax of the target language, so it may accidentally change indents, for example. Or it may change indents intentionally, but not the way you want it to. So the first exercise that I recommend you, and I will wait for your questions, is basically a very simple code generator. So you have an input file with field names. So there is a field, a type, and parser, which is basically a function. And you have the example files of this type in the source repository that I sent to all of you who registered for the tutorial. I can again put the link to this repository here. And I would like you to parse the CSV file using Cassava. Apparently, it's very easy. And if you have this input, then the generated parser will be something like this. So first you make declarations of what the input records look like. Then you insert the field names and types into the record as fields. Then you make a instance of toRecord and fromRecord for Cassava, and just tell Cassava to use this simple function main, which reads the CSV file. In this case, it should be not input CSV file, but example CSV, because input CSV is the format description. And then you use the decode function from Cassava to decode. Do you have any questions here?
Where did you put the
So I sent the link with the to the repository with exercises to tutorials 1 channel, which apparently has like 138 members. So hopefully all of you are present. The idea of this exercise, it's like very simple warm-up exercise. It should not take you more than like 5 to 15 minutes. It's just to notice the problems that I just talked about, and then we go to tomorrow. I wish there was a possibility for all of you to share screen so I can see the progress. Please write about your progress in the text channel, and then we can individually help everyone. Artem, could you pause recording until we finish this exercise, and then we go further? I see there are a few questions about a Cassava interface. So basically, import data CSV, and then you just need to define the data type, right? For now, we don't use the parsers yet. Just toRecord and fromRecord instance can be derived automatically. later on we can think about how to do a custom parser here. And the interface is that you just read a byte string into memory. So you read entire file with BS read file. This is from data byte string char8. And then you decode the input, which is basically entire input file as a string, as byte string, with a header option, right? So that the header is matched obligatorily. And after decoding it with the header option, you get an either error or the output, right? The output would be a list of records, a list of input records, and error would be just an error message. Does it answer your questions, Alan, or should I tell a bit more about it?
I've been pretty lost since the beginning of this exercise. I don't never understood what the objective was.
It looks like you're muted.
Okay, thank you. So do you hear me now?
Yes.
Oh, great. So basically here you have a skeleton code where you just need initially to change the field names and types, right? Using this CSV input. I used the CSV input because that means you just have a single. The CSV file can be basically read into field type and parser. So for now, you just ignore the parser. You just replace the field name and type in here and check with other input, one CSV, input, two CSV, different schema. Do you have any more specific questions, Alan, or do you have anything particularly?
I just don't understand the relationship between what you have here as output and what you have as those list of field names or something and what look like functions on the other pair muted.
Right. So here you have an excerpt from the Haskell module that is to be generated, right? And in this Haskell module, you have three main elements. I skipped the imports and module declaration, right? You can put it by yourself. I put the data declaration, the instance declaration for the same record, and function to test that your parser works, right? So the only thing that you need to change for now is the data declaration. So you can basically start by putting entire string like this into the output file, right? And then just change the field name has type string, field name has type int, field name has type day of week. The input is the same, name, age, and day, right? So in the input, you would have the field name, age, and date, right? Now we are looking at the input, right? Did I explain it, or did I just occlude the matter?
So you want to generate a one module with all of the data declarations from the input, or multiple modules?
What, just one module? So we are simulating the situation now that is just one module generated, because it's just, you know, an example of the problems that we will have. So normally, of course, you will later use it for much larger schemas, right? Here you have just one record with three fields, but the idea is that when you know how it works for three fields and what problems you have already in this input, then you will know how it works for more, right? So that's the principle of agility here. Very small code generator can generate you 1,000 lines of code. Maybe I go back to the skeleton code. You see that it's basically here, the input is CSV file with 3 columns, right? And besides the header in the first row, it has 3 rows with data, right? It's for name, age and date, right? And here we just generate the record with name, age, and date. David, do you want to say anything? Because I think you're muted.
Sorry, just trying to take a look at it. It's been a long time since I used Cassava, so I don't remember how anything works.
Maybe I should just put the example code of how to read the the input record, the schema in Cassava, right? We can do it on the shared screen, and maybe that helps.
Up to you. It would be fine.
Yep, I can demonstrate it on the screen so that you have a start. So, okay, so here we are in the repository, right? So here, if you look at it, there is already package file that will compile the examples and test when you implement them. So we can go into app x1 main pages, and it's really easy. So first we need to import data CSV. Something with intro here.
Yeah, it looks like you're going to need vector and byte string.
No. I already built it, right? So I basically have. What I recommend you is that in the other terminal, you just run stack test file watch. Right. So you can see how it works when you are editing it in a different terminal. That's what I would do here, and it's already built. So that's what happens in the other terminal. For me, maybe I will copy and paste the more interesting error messages for you in case you have similar problems. So here I will just edit. And yes, there is something broken about intro here. It's not the best time to fix the environment. So you import the data CSV. And then what you do is to declare the schema record, right? And in here, you will want to have everything that you see in the input file. So you can look at the input file, example input file in here. That would be basically a field with a string, which is the name of the field, right? Age with the, type. And here, for now, we will also assume string, and we will tell why it would be good to avoid it. But this is kind of simple starter, right? And parser.
You can't name it type.
Yes, that's true. So, okay. So now I don't think there are any problems here. And here we use the skeleton code from the presentation, right? So skeleton code is like this.
I assume you're going to want to derive generic on your schema record.
Right. I really just copy pasted it here, right? And instead of input record, we have schema record. And also derived from record, but for reading, only to record is important. Right now, it may tell us that it would like us to first know what generic is, right? So we say it's from GHC generics, right? And what BS is Well, it is from data by string car, and here we use qualified import to always prefix it with the BS.
Doesn't it use lazy byte strings here?
I don't know yet, because now it tells me that you need to derive generic, right?
I'm just saying that
basically,
that Cassava uses lazy byte strings.
right.
Data.bytestring.lazy, it looks like. I've used it, it's just been years.
Yeah, something. Okay, now we have more interesting error message. So now if we try to test it, we get something like this, right? So we see that it complains about vector. So we need to import data vector as the map defined. All right. And we add the vector to the package YAML. I didn't do it originally. I think I used Protobuf for the original solution. Okay. So, right. Okay. And now we are almost there. We just need to enforce the type here. So basically schema record IO, right? It's too polymorphic. Okay. So I think we also have a problem with the path here. Now if we, I think we should just put use the environment and get args. And for M requires control monad. Map M underscore from what before?
Right after get args.
Yeah, all right, you're right. Perfect. So if you run it now, it will just print the
schemas or something.
Yeah. Will print every. It should print. Maybe we first confirm that it's actually reading any file. Right. So that's the result if you run it now. Right, and now it's just to generate the output, right? So what we want here is here for we have, instead of showing show schema, so it would be this part. Would be show schema. And again, schema would be something like this. First we show it like before. And then we are supposed to basically generate the Haskell module from schema. So we can use this. And here is the skeleton code, right? So as a this is generated code with a given schema. Now the question how to generate the code, right? Make it simple. So for now we just generate the string, right? So we would have some kind of skeleton. So prologue and data record and epilogue, right? And in epilogue we can just put this, the main function, and so on. In prologue we probably put the module declaration, right? Or we can call it parser.
Your doesn't
nothing more here. Yeah.
Doesn't your epilogue? Sorry, doesn't your epilogue depend on the names of the schemas or something?
No. So basically, if you look here,
there's multiple schemas, right? And you're trying to do something with all of them?
We use only one schema at the same time. So the module will just use the single schema. We have multiple schemas because we want to talk about schema evolution later.
Oh, so the CSV file that you read only has one schema in it at a time?
Yes, only one schema in CSV file. Can you please make sure that your mic is not too close from?
I'm sorry.
So you see, this is basically epilogue, right? And for prologue, you have a module declaration and the import. And the data record is the only part that depends on schema, right? So we have something like this. So this we copy and paste. Maybe I switch back, right? So the initial epilogue would look something like this. That's first line. Last line, and here we use test example CSV as the actual. And of course, here you need to put some imports, like import data, CSV, everything that I have on the top of this file. Right? Data, byte string, lazy, kite, yes. Hope that will not confuse you that we use the same input data format and example for the code generator. But that was supposed to be as self-contained as humanly possible.
Now you just have to write this as a quine.
Yep. And you need to do the actual code generation besides the skeleton code is in here. For now, it's like hardwired, say, to output the same record every time, but that's not the intent, right? So this may be unchanged, but then this line and this line should be changed. You can also use to run the module that you just generated immediately and get the errors. So run a Haskell module, and here, what is the name of the module that we write? Generate schema HS. Schema HS. Let's see how it compiles. So you obviously need to, all right. Code. Right.
Data.
Yes, it does take the schema here. So as soon as it compiles, since this may be better skeleton code for you,
it won't compile unless you give data record an argument, even if you ignore it.
Yeah. Yes. So now your goal would be to implement this data record thing. So it takes a list of things that should be here. So this should be customized. Right? I think we need one more import for day of the week. And the skeleton should also include the thing that I wrote at the beginning, which is basically allowing to derive generic.
What package is the time the
Time.
day of week?
It's time. It's time. It's very standard package. You probably already have it installed. I'm not sure that it's distributed along with the GHC, but if you build anything, you probably have it cached. Just type. I think it should be already in the package YAML. If not, we'll add it. Note that when you are using the run Haskell module, then it will, depending on the environment, it should use the stack environment if it detects it. And we get the same problem here, which means that we need to say which print it is here. Note that whenever you run example with stack run example, I added at the end here the run Haskell module that will immediately test that the generating module is working in GHC. That's way to functional test basically code generator. You should immediately connect it to compiler. So convenient. So basically, here you have something like this. Skeleton code. It's like this. And then when it tests, it just detects that it doesn't know how to convert the day of week to CSV code. So supposedly if you use input 2, which should have, or input 1 maybe we'll make input 0 that is just using string instead of right. So we will say that no, we don't really care. It's day of week, and we call it day, right? Be consistent with the second slide. Maybe add this and also start by because this should be customized anyway or changed for the exercise. And here we give the argument to immediately test the parser.
On shortly. Sorry.
Sorry for the connection. I'm not sure entirely what happened. Probably the video. So to resume, I put this skeleton code that really has only 3 lines to change, right? So we have the module here. We have the input is already parsed. And in this code generator, you just, instead of hardwired 3 columns with string, int, and string, you just generate the record entry. And then we can talk about the problems that you already have here in this example on the inputs 1, 2, and 0. So I looked at the Edwin solutions. Edwin Can you please try to compile it with GHC and see what problems you have here? Or
I can try. I think I need to update my prolog to match what you have in your latest version. But,
yeah, because it will not work for the exact reasons that we will be talking about later. So it is close to the right solution, that's true, but it has these small issues that we will need to fix later. Or you can generate similar CSV parser in Occam if you are familiar with the CSV parser library in Occam. There is no really obligation to generate code in Haskell here, right? Since you are familiar with Occam, I would recommend that you try to generate Occam code and immediately use the Occam compiler on the generated code.
Okay, I'll try that.
And one bonus is that when you solve it in Occam, like in add the skeleton code in Occam, and I think I have enough of the Occam knowledge to just mention the issues here and tell you how to solve them. Unfortunately, fortunately, the basic issues will be the same independently of the implementation language.
Did we ever get this extra commas extension, whatever it's called?
What extra extension do you mean? A derived generic?
No. To let us put an extra leading comma. I don't remember.
Where? Leading comma. Where do you get a leading comma?
In lists. I think they didn't end up doing it because of tuple sections, but I can't quite remember the discussion about it.
It would be very useful for generating the record data.
Right. So generally, if you have a list of many things that are separating by comma, right? So I suggest that you use some kind of standard function here. So basically, you have unlines that joins.
Yeah, I guess
like
I need an
right.
intersperse or intercalate or something. Okay.
So you can do join record lines. It's actually standard, so you can do something like this. And you basically just put the first field and then intersperse, which means that you only put this comma in between two fields. You can check on Hackett how intersperse works. I think it's in data list or similar.
I thought you want intercalate instead, because
Yeah,
intersperse
maybe.
takes a single character.
Right, intercalate. Sorry for my mistake. So intercalate like this. So it would just take a list of strings and produce a single string. Right. And what you want to do is to just insert an end of line and then indent maybe 2, maybe 3.
But might be better off just using braces and semicolons.
Yeah, maybe. So generally, when you generate the code, you tend to use braces and semicolons for facility. If you want it to be read, you may actually use the document combinators like the pretty printing combinators, because these things quickly get huge. And by huge, I mean hundreds of lines where you want to understand the structure. And sometimes when you are debugging it, it's easier to debug the generated code by looking at it. So that's common in code generation and data science, that you want your generated code to be readable in case you need to fix it, unless you are like super certain about the results. But then I would recommend the presentation by I believe Dennis Ritchie about security of the generated code when you cannot find what it does. So these are all like typical issues. So you probably want to make a library of small things that merge the code. In serious code generation settings, we either use pretty printers or pretty printers on top of AST representation quite often, like intermediate representation, right? Just skip it here because they are to be quick exercise. So strangely enough, Cassava uses strict byte strings for unpacking fields and lazy byte strings for decoding. So you need to import both if you want to make the day of week instance. In case you didn't make it yet, because probably you did. Any other questions? I already told that I recommend read either from text read for many reasons. There is elaboration of why you should use read either, or even better error reporting in case of functions that read anything longer than a few characters, basically because you want to find the error and you want to know why it happened, that it failed to parse, and read maybe doesn't give it to you. But for read maybe and read either, you need to first BS unpacked, so unpack byte string to string. That's basically this instance here on the screen that I highlighted. First you BS unpack and then you use read either. For elaboration on read either and maybe a little bit in context of Agile data pipelines, you can look at my Haskell lab. So dear participants, how is it going? So what are the most common errors that you have besides Cassava? Edwin, can you tell what your question is?
I'm sorry, I had a little trouble copy pasting. So I got that error from Haskell. I'm first trying to make the Haskell generator work, and then I'll switch to generate a camel. So it tells me that there's something wrong with the derived generic. So maybe I missed something from, maybe I'm missing that language derived generic.
I think you got syntax slightly wrong. So this closing brace should be indented by at least two columns or one column. Right? But it's generally easier to generate the code in a language that you somehow know that. So I recommend starting from generating the OCaml code, and then I can show you, or you will see the errors actually from the compiler immediately at what they point, what is wrong with this example input and how you can handle it. David, Yiyun, Alan, do you have any further questions? Or is it all resolved? I see we have a first person who completed the exercise 1. Thank you very much, Alan. I think I would help you to complete all the exercises, but we'll start talking about the issues you may already see when you are finishing the implementation of exercise 1 yet. All right. Or do we have anything that I should still tell you about? Awesome. So I can expect Ian and Edward will be probably next completers. That's awesome. So meanwhile you are finishing, I will continue the presentation, but please post a gist whenever you get a solution. That's awesome, really. You see that we may have problems. You added the line numbers to the error messages, but you still need to take care of field identifier conversion, right? So for example, in the code of Alan, this conversion was done by basically mapping to two lower field function, right? So each field name should be starting with the lowercase. It's not necessary to convert the entire name. But the problem may be that in the input you have case sensitivity. So you have two field names that only differ by using upper and lower case. And how do we resolve it when the target language doesn't have the possibility of using the uppercase as the first character, right? So we will talk about it in a minute. The second thing is that we added imports, right? So it would be good to gather imports whenever we need to add them separately. I normally just recommend using the writer monad. So as you probably know, writer monad is used for logging, so you can only add things to it. And in this writer monad, you can have the things that is basically monoid state. And in this state, you can hold as one thing fragment of generated code, and as the second thing, a list of the modules that you need to import for this code to work, right? So I can give you the example of this from live code. Here, because this is useful technique of basically holding together generated code and some additional information that you need to get the final result, right? So this is example from the wild. Now we see here we can write module in several languages, and sometimes we don't have the just module to share. Sometimes we want to share the code fragment, right? So we use one code generator inside the other. And then we use this code frag type. Basically holds the code, which in your case will be the string. Sometimes you add the phantom type so that it is apparent what it refers to. Then the list of imports and the list of packages that you need for this code to work. This is for larger projects where you basically generate entire package, right? Not just entire. Okay, so now we can come back to the presentation. So the next issue is the testing of generated code, right? So what you frequently see in code generators that just start to be tested is the unit tests that are like, you know, for this input, I have this exact output. And the main problem with this is that it's very fragile tests. So you may change, for example, one import, right? Some hardwired import or a style in which you are doing something, and it will ripple over to thousands of tests if you have so many, right? So that's not a good way to test code generators. When you test code generator, you should have a separate statements, assertions about what happens with generated code, like separately say that there is a module declaration in, like module main, right? A separate assertion that you generate the main function, separate assertion that you generate the data record. And it looks difficult, but Haskell gives us tools to deal with it very quickly and very easy. I suspect that other languages also. So basically what you can do is, besides this crude functional test that you already presented for you, which is basically run and compile an entire module. But it's not a unit test. It's not single assertion. So it will be good for like end-to-end testing, but it's not recommended as the only way of testing. You want something fine-grained. So besides that, you can use quasi-quotation, right? So quasi-quotation is the mechanism that you can use in Haskell to insert any target language syntax, parse it into either pattern or expression, and then reason about the target code inside Haskell, right? So you can, for example, you can say that you define the plugin variable. Here we have a v1 as a placeholder for meta variable. So this is kind of reserved syntax in our case. So we never use v underbar something for real variables. It would be even better if our parser would allow us to put the $ in the beginning of variable name, but we want to reuse existing parser. So you have hundreds of parsers for different languages on Arch already. So I wouldn't start a small project, small code generation project by implementing a parser for a larger language like Haskell or C, or I don't know, Prolog maybe is not that large, but anything larger than X as expressions is a waste of time. And if you believe that you should use libraries whenever you can, then even don't implement a parser for S expressions. Just you reuse the existing parser. So what you make is basically quasi-quotation. And here between this D and the closing braces, so you have a bracket. Yeah, so you have a square bracket and then D and then bar, and then again bar and closing bracket. Everything between is parsed by the parser during the compilation, and this can be then made into a pattern, right? So we can make assertions like generated string should match plugin variable, which basically means that after we substitute this variable name, it should be able to use you should find this declaration somewhere inside, right? And then you can make single assertions like this should be declared, there should be expression a plus b, and so on. So that's the recommended way. Use quasi-quotation and then use the existing parser for the language to match the fragments, to analyze the fragments of generated code. There is a library that we put on Hackett, which is Haskell src match, that will help you with that, right? But it's very easy. If you look at the library, there is very little code inside there. And this is actually something that a lot of people use. Maybe I will also refer you to the blog post of ETSCO that is going further into how to implement it. So this is how to implement with from ETSCO. So he doesn't really mention existing parsers, but that's my recommendation. There are many parsers already on Hackett, so you just take existing parser and replace the variables according to some key with the variables in Haskell. Right? So next thing is that sometimes we generate from rather large and complex languages, right? So one way to do it is to make unit tests. Second way to do it, but it's a lot of effort, right? For a large language, good unit tests, that's a lot of effort. Second thing is to just parse the large examples from the wild and hope that everything most important will be there. That's very agile method because you don't do much work, right? But it doesn't give you the coverage. Luckily, in functional programming, we already know that there is another method that is very good and is widely used, which is basically property-based testing. So you try to make valid inputs in the source language, and you just randomly generate them, and then you will get hopefully better coverage for basic constructs and basic combinations thereof. There is a simple example of it in JSON autotype repository. In the presentation I sent you, you can just click over this and you will be taken to the example, right? There is a paper about it from Pauka and Hughes. And there is also a paper on using quick check for testing compilers like Occam compiler. That would be very useful for this. So basically, in each case, they report, especially here, that surprising thing is that they report quite a lot of bugs in the compiler that they found this way. You can also use American fuzzy loop, but the problem with the American fuzzy loop is it works independently of the language, but it probably most of the time will not generate the well-formed inputs for you. So that's a different application here. You are interested that in input that is always valid, but that may break the code generator, right? So next, I recommend that you use this testing method to extend. When you finish this generation of the code, you just test using Haskell SRC match. And these constructs that I've shown you here, that you have, for example, main function, that you have the data input record, the basic things. That's very easy, and that will give you some confidence that, you know, don't break entirely. So that would be the goal. By the way, how are you doing with the finishing of the first exercise? I'm actually waiting for your questions because now would be the time to do the second exercise, right? Unless you want me to move on or tell something. We are now at exercise 2, right? So the idea is to check for small properties of the generated code using Haskell SRC match, like that it contains some plugin variable, or in this case, main function, that it contains the record declaration for input record, that when you put the input in the list of the fields that you should have, the field with a given name, that this name is correctly translated. One important test here would be to try to use quick check to generate data fields and types randomly. So data field name could be any string, and then you can check that you generate valid Haskell identifier. So meanwhile you are testing, I will go on. Exercise 3 will be independent of exercise 2. So you can do part of exercise 2 and then start doing exercise 3. If you have any questions at any point, just ask me. I will help you to solve exercise 2 too. So the idea would be that you are fully able to apply all these suggestions to your code generation project after this tutorial. So now I will, while you are solving the exercise 2, I will talk a little bit more about identifiers. You already noticed that you know, different languages have a different idea of what are valid identifiers, and you need to translate them. And sometimes that may be as much as a few hundred of identifiers, and some of them are from different namespace and mean different things. So for example, Haskell type identifier can be the same as Haskell constructor identifier, right? But these two identifiers mean different things, which means that they should mean different things in generated code, but they also need to be translated into different identifiers in the generate. So the initial attempt at translation of these identifiers would be like Alan did, would be with the basically using to lower, right? To lower for functions, to upper for types. And you have valid identifiers most of the time. The problem is that sometimes you need to remove characters. So these translation functions get more and more complex. I recommend you to create a single function for each pair of source language and target language, right? That takes additional argument that describes the namespace in the source language that you have. So in our case, it would be in CSV in the first column. We don't have really a language there, but sometimes you have. And then the target language in our case is Haskell, right? And that is because, for example, if you are generating Haskell code from C code, which is, I would say, uncommon, but a good hypothetical example, not much different from generating SQL from Haskell. You will have the function changelog status that starts with lowercase, and then another function which starts with uppercase, right? You will have type that starts with uppercase, but it has a star at the end, right? Specifier for the pointer. And then the argument that is lowercase and sometimes uppercase. There are conventions, but they are not always followed. So basically, we will define the data type to define each of the namespace choices. So for Haskell, the basic namespaces that we need would be NS types, so pure types, NS constructors, and NS functions. Usually in code generation projects, we do not go very far into data kinds, but in case you would, then it would be slightly different. But now, for simplification, we just have types, constructors, and functions. We ignore modules and so on. So that's Haskell 98 single module. And the generic, fully generic translation of GHC from the Haskell identifier to identifier for linker is something like this: text ZM1 ZI, 2 ZI, 3 ZI, 1 data ZI. Okay, that's pretty long and definitely not easy to understand, right? So you would like to avoid this type of identifiers if you are generating this to be read by anybody but another compiler, right? So for example, you may be generating parsers that need some kind of review occasionally, or the code that, for example, would have data declarations that need to be read as a documentation by humans. So not all code generation projects are compiler projects. Some of them will generate the code that will be read, right? So for this purpose, you want some better identifiers. How you can do this? So first, you take the source and target namespace as an argument. Then you can take a list of descriptors as a list of strings that will be telling you optional information about the identifier, right? So first you put the function name, say, in the other language, and then where it is, what are its arguments, and so on. And pass it all as a string, and you just use the string from the beginning of the list until the end, but only as much as you need. So as little as you can. And you use the state monad for code generation. So you keep the map of translations that you already have. You can also have a set of used up identifiers in each target namespace, so you never duplicate, right? And then it's pretty easy to add something to this map, to check that you will not use the same target namespace identifier for two different things in source namespaces. And you can just use the translate function each time that you need identifier in the target language. And also you can, in this type translate function, you can make any validation. So for example, you would remove any character that is invalid in the Haskell identifier, like backquote, for example, right? You can replace it with underbar or with nothing, because you will always have extra descriptors to add. And if you run out of the descriptors and you cannot find a unique name, you just add the number at the end, like 0, 1. Then you will have infinite supply of the identifiers that are short and relevant to what you are doing. These are humanly readable. So for example, the first time you translate example in the alpha and in the main module, you would get into NS constructors namespace, Haskell constructors namespace. Then you would get example uppercase, right? Only first letter needs to be uppercase. The rest can be anything. Then that's short type name, right? Then you translate example with additional information about the parameter, which is gamma, in the math module. And then you use example lowercase, because you can check in your code generation monad state that this is unique identifier. That's why you can put it so short. And then when you have another function that is somewhere nested in the main module, and it has argument delta, then you can use this argument delta as additional information that will point the user into where it comes from. So you say example delta, right? And then when finally you translate example again into NS functions namespace that already contains example and the example delta, then you just add a number, example 1, right? You may want to dump this translation of identifiers just like JavaScript source mappings are. So basically make mapping from the source identifiers to target identifiers, and then you dump them for easy perusal, just a CSV file, right? With the source locations of each source identifier. That would help. Along with locations that you put into the target code that you generate, that should be sufficient to easily debug things and simultaneously have short human readable, and definitely better than this identifier from GHC, which is just, let's be honest, scary. It's so long, it's scary. Humans usually prefer to read at most 3 words in identifier. Right? So the next serious topic in code generation is versioning. So we have a code generator like here, and you change the schema from which you generate the result. And the problem is sometimes you generate the code and then you release it, people start using it, and then you have another version and people start using the second version, right? And then they start seeing differences and it breaks and they get crashes or something. So that is to be avoided. They should at least know that they use the wrong version. So the first thing for versioning that you can use, the simplest, is basically during code generation, just like you insert in the beginning of the file the information, this is auto-generated code, and then you insert line directives or line pragmas so that it's known where it comes from. You also insert metadata. So all compilers nowadays do insert metadata about who compiled it and how it got there. So you should do the same, basically. So where was the input, when it happened, and if you have a Git version of the code generator, you just put it here, right? Maybe you also have human readable same version that would also do. And this is a cheapest approach and easiest to apply, right? For example, Unison uses this approach, and it quickly illustrates what is good and unfortunately what is a deficiency of this approach. So Unison is a file synchronizer, so you can see people using it on very different machines. It's compiled in Occam from Occam source, and the generated code uses the protocol, right? So in this case, the code generator is Occam compiler protocol that basically serializes the Occam messages, and they are exchanged between two Unison instances, one on the server and one of the client, and they communicate to make sure that you have the same version of the file. And it's excellent synchronization program. It works much better than Dropbox synchronization, for example, or async, because it allows you to interactively fix the files. But you really have to have exact same compilation and exact same Occam version on each machine, which may not be feasible because maybe you have a new Mac and an old Linux, and you cannot upgrade the old Linux, and you need to compile the new version of Unison on old Linux, or old version of Unison on new Mac, right? So that's not the best solution. That will break often. That will basically tell why it breaks. So it tells you have incorrect version, I failed to work. But it will break often, and if you make a lot of small improvements to the code or cleanups or do a lot of maintenance, that doesn't really change a lot in the result. It's not what you want to do, right? Because that's basically breaking the abstraction. So what you may have also is that you basically save you know that only few files have the interface, like the types of messages in Unison, or in our case, the schema, right? So only few files have the schema that affects the code generation. And then whenever you have a new version of the schema, then you mark it for release, or you automatically compare if this particular file, and then you put this version. And that's better solution, and that's also very cheap, and that's used by pandoc types. So basically pandoc is this generator that basically makes documents from many formats and puts them into many formats. And it's not code generation per se, except when it generates LaTeX, but it uses the plugin interface to get filters that do a lot of clever things. And these plugin filters need to basically use the versioned interface. So pandoc is upgraded often, but pandoc types rarely. So this is the API. If you can, and then I would recommend that your code generator also limits its interface of generation that may change and break things. In compilers like C or C++, the ABI, or application binary interface, changes very, very infrequently, right? That's major breakage. So they also use this method. And this is sufficient for many purposes if your interface really changes very infrequently. However, if you expand the interface, then you run into trouble. So what I would recommend when you are generating, say, you use your generator that you wrote on this tutorial, and you have different schemas in input 1 CSV and input 2 CSV, right? Or input 0 CSV and input 1 CSV. I would recommend that you read both old interface from which you generate the code, and the new interface, so new schema, and compare them and show the changelog at least. So we generate not only the code to be executed and compiled by compiler, but a changelog for people to have information of what changed about the schema. And if you still change things infrequently, you have infrequent change of schemas, and usually they will need human intervention anyway. That may be. However, if you change schema relatively frequently and you want to migrate a lot of data later on, then you use the database migration style. So besides generating changelog, you may want to make a script that automatically migrates the programs from old versions of the generated schema into a new version. So this is the same approach, but fully automatic. So I would recommend as exercise 3 that you generate a changelog from input CSV and input 1 CSV, any of these input CSV files. This is very small change, and just compare how it works. Any questions about the exercises here? Anybody wants to show off the exercises already executed? Hey David, did you make any progress with the exercises?
Asking me?
Yes.
I never finished up number 1. Things have been a little distracting, and I got very much confused about what you were talking about with number 2. So no, not really.
Because I got scared because you got label job market just after asking the last question. So it seemed a little bit too much of a like COVID crisis, right? When everybody searches for the new job. But this is just a tutorial. Anyway, besides telling bad jokes, I can tell that everybody can fill in these exercises now or later. And if you fill them later, just send me the result, and I will review it for you. And if you have any code generation project that you want advice for, just let me know, right? Because maybe you start the exercises now and just complete them later. That's all right. You should have my email along with the materials I sent you. And Crystal, I thought that I still have an hour to spend, so I have few more slides. Unless you think that I should read. So if you want, I would continue with the 4th exercise and summary of how to make Agile code generation project, but I would really encourage you to make this exercise 3. It's again, it should be very simple. It should be 15 minutes. It's just that the first time you do anything, that always takes longer time. So we've been talking about quasi-quotation a little bit before. Here are a little bit more of examples of quasi-quotation, how you can use them. So you can use them to generate the Haskell code inline with template Haskell, like here. You can also make a quasi-quoter that is basically using the existing parser to make expression in Haskell, and then this expression can be reused. So this is basically using this square bracket bar syntax. And between this first opening square bracket and bar, you have the name of quasi-quoter that is actually Haskell function. Many languages have a similar quasi-quotation facility. In particular, those of like Lisp's icon. And to construct the Q expression, QX that is the result of quasi-quoter, it's easiest to use the template Haskell inbuilt quasi-quotation, which is without any name. And this means that it should be parsed as Haskell expression. So for example, here you would have an argument, and D is Haskell declaration. quasi-quotation, and you just insert the name of type A and type A, right? Here it's similar. The quasi-quotation is SQL, it parses SQL and allows any $ID to be replaced by Haskell variable. It's very simple to make a quasi-quoter when you already have the existing parser of the language. So basically you take this my parser that either returns an error or AST. You define a quasi-quoter as the record from language Haskell quasi-quote. And you take argument and apply my parser to this argument. I think I missed the argument here. Sorry for that. There should be argument as a lambda before do, after quote exp. And then apply to my parser. And then if you have a error message from parsing, then you just fail with the error message. And if not, you use the lift function. The most convenient way is like Scott de Vries have written on his blog. There is also a link for you here, so you can go into details. So the most convenient way is to define lift as a class. So lift is converting the AST from your language to the Haskell Q expression or quoted expression. And usually defining lift is very easy, so you just make it descend through the ADT of your AST, abstract syntax tree. So for example, if you have add, and there is AST on the left and on the right, then you make an expression in Haskell by using this Haskell quasi-quote. So you basically use this anti-quotation or reference to the variable lifted AST. So basically you need to lift AST1 and AST2 inside, and then add the actual Haskell plus operator. So you make a Haskell expression in a very easy way. It's like just writing an interpreter. It's very similar.
Are lift and lift-e two different things? What's the...
lift is the name of the class. Lift-e is the name of the method.
No, I mean the lift-e and then lift.
It should be the same. You are perfectly correct.
Okay.
Thank you for pointing it. I changed my mind because originally I only wanted to note the quote expression. And now I will tell that basically if you are making quote path, quote type, and quote deck, you just make similar function as lift-e, lift-p. And instead of using this quasi-quotation for expressions in template Haskell, use the same quasi-quotation for patterns. There would be p here, right? And then you have a lift-p function in lift class and so on, right? Not only lift-e, lift expression, but also lift pattern, lift type, and lift deck, whatever you want. Is that clear, David?
Fairly. I mean, I don't know what it means to lift a pattern, but you're muted.
So the pattern and expression, that's basically like left hand and right hand of the case arm. So here you have expression, right? Error message or lift AST. This is Haskell expression. And on the left hand here, you have left message and right AST. And if you want to pattern match on some other language, not Haskell, you probably want to also make a quasi-quoter for the pattern. And then you define this quasi-quoter by the means of lift p, which is basically similarly defined as lift e. But instead of addition, you only have the things that can occur in patterns. And instead of this opening bracket without any identifier, you have p. And also variables are quoted as var p. So pattern variable instead of expression variable.
Do you have a particular template Haskell tutorial you recommend? Both reasonably up to date and also reasonably introductory, and I haven't found it yet.
I think there was template Haskell tutorial like 2 or 3 years ago for ICFP, but I agree there should be another one. So I think that a lot of people are using template Haskell, so it's like growing in applications each year, so should be updated. I will send you a tutorial with materials if that is all right after the presentation.
Sure, thank you. I mean, even just something in text would be fine. Just
yeah.
The original paper's, reasonable but out of date, and then everything's changed, and I don't know where to find the.
Not as much change. So some things are changed, but what you mentioned in the paper are different from the things that you first want to talk about in practice, right? So the first thing is like defining quasi-quoters that is just mentioned in the original paper. And then the second thing would be using like run queue to debug the patterns, which is not mentioned in the original paper at all so far. So yeah, definitely I will send you. So I would recommend as a final exercise that you make a quasi-quoter for your chosen language. So I just take the parser from the package. You don't write your own parser, you don't need it. And use existing parser to make a quasi-quoter and for example, pattern matcher on the language. That can make it much easier to work with the language if you use quasi-quotations to generate the code instead of making a complex intermediate representation by hand, right? Because usually intermediate representation has many additional things. For example, one can just use GHC parser lib to implement the test matcher that we have in Haskell SRC match. You can look also at the code of Haskell SRC match. Maybe you can even simplify it. It's very short, like 2 screens. So now that was supposed to be like the last topic on the tutorial. So do you have any questions, or should I just summarize?
I would have one question. It's more of a practical nature. So you mentioned we use these line numbers so that we know where the code comes from. But in case we make a mistake and there is a bug in the generated code, sometimes then it tells me a line number from the original source that doesn't exist anymore, because of course there are a lot more generated lines than source lines. So it's a bit difficult. In some cases, it would be useful to know the line number from the generated code so that I can look up what the mistake is there instead of the line number from the original one. But sometimes if the problem comes from the original language, then it's useful to know the line number from the original language. So I don't know if there is a way of keeping track of both, or depending on the situation, should I just enable and disable the line number generation?
So yes, option to enable and disable is one thing that people use. And the bidirectional code generation is the second thing that people use. So, besides the line pragmas and line directives, you can basically try to make a change in generated code that, that fixes it, and use bidirectional code generator to backport this change. But so far, it seems that making a bidirectional code generator is a little bit more effort, right? Does it answer your question?
Yeah, thank you. Yeah, definitely, if we get to writing a bidirectional one, then we can fix any bugs in the code generator by fixing the output. And then if at least the backport part of the code works correctly, then we can also fix the code generator itself. Yeah, I haven't got so far in my example yet, but I see where you want to go.
So yeah, I hope I shown that bidirectional code generation is not black magic. So it can be relatively easily done with this marker. So we basically have a marker like line pragma or line directive, but the marker for the code generator at the beginning and at the end of the generated fragment. and that's all you need. So it works very similarly. It's just more work because you need to do it in both directions, right?
Yes.
Alexander have asked the questions whether compilers tend to add metadata to all identifiers. Well, most of the time, the metadata is put for each file. So just everything that is common for entire file. So for example, if you see the Python pic or GHC generated object files, you will see version of the compiler and so on for entire. However, when you want to debug the things, that becomes insufficient. So that's one of the differences between pic and PO, Python object files, that in Python object code generator usually removes superfluous information like documentation or the references to the original source code. So references to the original source code are present in case of Python bytecode generator in PYC file, right? Because you want to debug things. So generally you keep all the metadata if you want to debug things, in particular source locations. Does it answer your question, Alexander? Yes, Alexander, that's true. Strip command basically removes metadata, most of the metadata. I'm not sure if it removes all. I suspect it removes most of the strings that are not referenced by code. And usually metadata is kept as strings. Sometimes some compilers put metadata as structures in memory, right? And then it depends whether strip command knows about this particular identifier as being metadata. Any other questions? So with regards to monoid, I recommend using monoid when it's unambiguous, because basically it is better to use less function names and less methods. So when it's easily understandable that these two things can be merged and put together only in one way, then using the monoid, straightforward monoid is the best thing. Also, monoid has a lot of functions that work by merging the monoid values together, right? So that means that you can use, for example, all the foldable things, or for example, you can use the writer transform. Edwin asks, are there similarities with versioning for code generation and for RPC protocols like Protobuf? Would you think Protobuf or similar serialization help with the version upgrades? Yes, that's one of the problems that Protobuf exactly matches here. So if you are generating Protobuf, then you have an interface description in there, and only the changes in Protobuf need to the change of the code, right? So this is exactly solution that matches the version 3. So you can actually make automatic migration for most of the data in Protobuf format, for example. Because I don't know if you observe, but mostly when you add the feature to the protocol, most of the conversations in the protocols will not really change that much. That's the same like with database.
Because I think there is a related presentation called Essence of Live Coding. I didn't watch it, but I just quickly skimmed the paper, and it also mentions the possibility of doing live hot swap of Haskell code and doing the data migration mostly automatically. That would be an interesting thing to see how to link with your code generation framework.
I would actually recommend using essence of life coding style of approach if you have a program with extensive state and you are debugging it, because it does very elegant migrations of the state. So it is a further step in this direction, right? Since it's fully dynamic and fully automatic and generic. So that's the next step. So I would go on considering agility in case of code generation project, since a lot of people already use agile methods, and agility is considered in many settings. So I would like to reference that. So basically, the idea with agile software development is to minimize the process and only make the process such that you can maximize the outcomes. So, you, for example, put undefined if you don't know if you need to define something. It's not about safety, it's just first you get the working thing and then you make sure that it really works, right? So this is typical for business setting and for trying to get the outcome as soon as possible, right? In the context of code generation practices, we can just judge all of these practices that were mentioned by their cost and assume that everything that has negligible or small cost should be always done. If the cost is per target language and we plan to make multiple generators for the same target language, then we can also divide this cost between different projects. So that's also important to share the effort. And here is basically the simple table of the things in the order that you should implement them, without yet placing the essence of life coding here, because that's also a worthwhile approach. But not all code generation projects can use this fully generic approach to migrate. So I would say that commenting and source locations and basic versioning is just minimum that you should always use, because the cost is really negligible. In case of identifier minimization and unit testing by matching fragments with quasi-quotations, I would say in this case, unless you have very small student project, then it's worthwhile to use both techniques at all times. If you only have a 1 month project, maybe you don't want to put the effort into it. But when the project scales, if it has the time to grow, then you probably will gain a lot by just using this approach, because it's higher level language for code generation. In the case of random input testing and type checking and migrations, these are two things that may require effort if they are not generically implemented. So I would look either for possible generic solutions here. There is generic arbitrary for quick check and generic migrations with essence of life coding. But here you put the effort if you feel that you really have a lot of bugs and you don't know where they lie, in case of random input testing, because input language, unless the input language is small, like it's JSON, then you just make random input testing in a generic way or within 1 week. But in case the input language is large language like Haskell or C or OCaml, there are success stories for random input generation, but generating valid and only valid Haskell programs is a little bit complicated, because they need to type check and so on. So here you may want to weight the gains and the effort, depending on the size of your language. Do you have any suggestions or or questions about that? So I would stay here to answer any questions that will still appear on the chat. I encourage you to complete all the exercises, or even just those that you want to complete. I will now review the exercise from those people that already sent me something. And please remember that code generation, in case you have a reproducible, repeatable task, may be much faster than actually writing this code manually and getting bored by repeating the same steps. That's my makeout. Again, best wishes with your code generation projects, and feel free to message me at any time on the chat so I can help you with your project or exercises. And that I would sign out now. See you around on IC.